In this screencast we will focus on the air-water system and explain how to use the Mollier diagram. The Mollier diagram is also known as a psychrometric chart. We will go through composition as water content and partial pressure water, enthalpy and temperature, relative humidity, wet temperature, adiabatic saturation temperature, wet and dry density, heating and cooling, and how it relates to dew point, adiabatic mixing, and finally mention air conditioning. So why do we study the air-water system? Well, understanding the air-water system is important in a lot of environmental and climate problems. So climate change, effects of ground level ozone, and so on. But it's also important in a lot of technical applications like air conditioning, drying, cooling towers, absorption, and so on. And if you want to save energy, it's good to know the air-water system and understand how it works. To be able to understand how the Mollier diagram works, it's good to understand first Gibbs phase rule. So Gibbs phase rule states that the number of phases plus the number of degrees of freedom equals the number of components plus 2. So for moist air, we have gas, 1 phase, and we have water and air, 2 components. We get 3 degrees of freedom, which means that we have 3 independent state variables, for example, pressure, temperature, and composition. And X here is the composition expressed as kilogram of water per kilogram of dry air. The Mollier diagram is an enthalpy water content diagram, and it's also known as psychrometric chart, and it's drawn for a specific pressure. And since Gibbs phase rule stated that we have 3 independent state variables, and we draw Mollier diagram for a specific pressure. We already used 1 state variable, and then there's only 2 independent left. So that can be enthalpy and composition, or it can be temperature and composition, or temperature and enthalpy, and so on. And the nice thing with the Mollier diagram is that if you know the pressure and 2 other state variables, you can easily check what the other state variables are. So we start by drawing X. So the vertical lines here represent a constant water content. So this is 0 and this is 0.05 kilogram of water per kilogram of dry air. But before we also draw the enthalpy, let's first realize that the composition can be drawn also as the partial pressure of water. And since we draw the Mollier diagram for a specific pressure, we can easily calculate the partial pressure of water from the water content by using the molar weight for water and the average molar weight for air. So this is the equation going from water content to partial pressure water, and this is the one going from partial pressure water to water content. Okay, so we can draw that line here and say that 0.03 kilogram of water per kilogram of dry air is more than 40 millibar. So, and you can of course measure here more exactly what it is. Okay, and it's these equations here. The second axis is the enthalpy, and for ideal gases the enthalpy for a mixture equals the sum of enthalpy for the components. And gas mixtures are usually ideal and liquid mixtures are seldom ideal. So since we have gas, we can rather safely assume that the enthalpy is the sum of the components. And remember from physical chemistry that enthalpy is independent of path. That means that if you have liquid water at 0 degrees and want to create water vapor at 100 degrees, you use exactly the same amount of energy if you first heat to 100 degrees and then evaporate, or if you first evaporate and then heat. So the relation between enthalpy and water content, note here that water content is kilogram of water per kilogram of dry air. So it's a ratio between the 2 components. A bit odd unit, but that's the usual unit to use in these circumstances. The enthalpy, if we first evaporate and then heat, we get this equation, where this Cp here is the heat capacity for dry air, simply times the temperature in Celsius, using 0 degrees Celsius as a reference temperature, and 2500, that's the evaporation enthalpy for water at 0 degrees Celsius, and times the water content. And then we heat the evaporated water, so we take the heat capacity for water times the temperature in Celsius, since we use 0 degrees Celsius as the reference temperature, and then times the composition. A problem with this equation is that the heat capacity varies with temperature, but usually that's actually ignored when drawing a Mollier diagram. So that's slightly wrong, but reasonably accurate at least. Okay, so we draw the enthalpy, but we choose not to draw it orthogonal to the other axis, but rather slanted like this. So note that it's not 90 degrees between the axes. And we actually choose to draw this slant in such a way that the line for 0 degrees Celsius becomes exactly horizontal. So we have this equation here, which relates composition, temperature, and enthalpy to each other. And we slant the enthalpy lines such that the 0 degrees line becomes horizontal. You can look here at the 50-degree line and see that that's not horizontal. It's slightly higher here than it's over here. Okay, so I didn't draw long lines here for -10 degrees and 0 degrees. I stopped here. There's a reason for that, and we'll explain that when we explain about relative humidity. If you have steady state, then the partial pressure of water must be less or equal to the vapor pressure at that temperature. And the vapor pressure is given by Antoine's equation. You can look up A, B, and C in a table somewhere. Please note the units. It's rather common that you have temperature in Celsius in this equation for some reason, and then you have to look up what kind of unit you should have for pressure for that specific numbers for A, B, and C. And the relative humidity, that's defined as the ratio between the partial pressure of water and the vapor pressure. So the partial pressure of water at saturation, that's why we call it PV sat here. So we get this kind of lines here. The line down here is simply Antoine's equation. And that's why we didn't draw the temperature lines any further. We stopped here. The other lines here are the relative humidities, and that's given by then the partial pressure of water divided by the vapor pressure. So this is 80% relative humidity, and this is 40% relative humidity. Okay, time to test your understanding. If you have a moist air in equilibrium with liquid water, how many degrees of freedom do you have, and where are we in the psychrometric chart? Please pause here and try to figure that out. Okay, let's go back and look at this one here. Now, if you recalculate how many degrees of freedom you have using Gibbs phase rule, you will see that you have 2 independent state variables rather than 3, since you now have 2 phases, liquid and gas. So where are we in this diagram? Well, if you know only one more state variable, you have the pressure, since this is drawn for a specific pressure. If you know the temperature, for example, you should be on a specific point. And when could that point be? Well, if you are in equilibrium with liquid water, then the partial pressure of water must equal the vapor pressure. So you must be at this point here, 100% relative humidity. So if you don't know the temperature, you know that you're on this line somewhere. And then if you know, for example, the enthalpy, or if you know the water content, you can find out exactly where you are. That means, of course, also that if you have a moist air that is in equilibrium with water, and you know that the enthalpy is 40 kJ per kilogram, that means that it can't be 0.03 kilogram of water per kilogram of dry air, but that it must be something like 0.01 kilogram of water per kilogram of dry air. Okay, time now for wet temperature. I don't know if you've thought about this, but If you take a shower during the winter time and have an open bathroom door, it's easier to freeze than if you do that during summertime. And why is that? Well, when you shower, you get water on your skin, and some of that water will evaporate. So you have air blowing past your skin here, and you have water on there, and there is a certain temperature of that air and a certain water content, and as it passes, its temperature changes and its water content might also change. Now, to evaporate that water, energy is needed, and you can calculate that energy simply through the mass transfer times the evaporation enthalpy. And you know from before that the mass transfer can be calculated using a mass transfer coefficient times a difference, and let's express that difference as the difference in water content. Now, the water content close to your skin, close to this water surface, should relate to the vapor pressure. So the water content that you have at 100% relative humidity minus the water content in the air. So the skin gets colder. Well, when the skin gets colder, then the temperature of the air here will be larger than the temperature of the skin, right? So that means that there must be a flow of energy from the air to the skin. So the skin gets heated by the airstream. And you can calculate that if you know the heat transfer coefficient, simply by multiplying the heat transfer coefficient with the difference between the temperature in the air and the temperature of the skin, or rather this wet surface. And you can juggle around with this and realize that this means that we will get a balance when the energy needed to evaporate the water is actually taken from the air. And this is this balance here. Okay, you get a wet temperature, and those are these green lines here. And you can also get here, if you have ice instead on the thermometer, ice can also evaporate, but you get slightly different slope here. It's important to note here that the slope of the wet temperature line is different from the enthalpy line, and that can be seen here, for example, where it's closer between the lines here, and up here it's larger distance between them. Now you might realize here that if you take 20 degrees here and you go to the saturation point, you see that at that point you also have the wet temperature 20 degrees, and that's not so strange, because if you look at this equation here, if you are at this point here, that means that this difference here is 0. So then this entire term disappears, and then T wet equals T. So when you shower, why do you get colder during winter time? Well, the thing is that usually you take air from outside and then heat it to your room temperature, and during winter time it's colder outside, and if you have the same temperature indoors wintertime and summertime, you get rather huge difference in wet temperature. So wintertime we heat maybe for something like 2 degrees one day, and then you get something like 11 degrees if you heat that air to 22, 23 degrees. It's of course dependent on how moist the air is outside, but you can note here that when it's something like 2 degrees, you can't have that much water as you can if you have, for example, 21 degrees outside. You can have much more water. So the summer temperature here, if you have this moisture outdoors, you get 17 degrees instead. What about adiabatic saturation temperature? What is that? Well, to be more precise in our definition of wet temperature, the wet temperature we get when the contact between the air and the water is so short that the water content of the air is essentially constant. The adiabatic saturation temperature, however, there we should have a long contact time such that the air reaches the saturation point, and then you have to do a setup here where you pump water and you have to add water, and the tricky part here is to add water at the adiabatic saturation temperature. So you will need quite a lot of trial and error to get this right. So you add with a certain temperature, and then you check what temperature you have here, and then you slowly adjust till you get the same temperature there as you have in the input here. A nice thing with adiabatic saturation temperature is that for the air-water system, that's essentially the same numerical value. For other systems, it's not the same. For the air-water system, we usually talk about two different densities. We talk about the dry density and the wet density. The dry density is kilogram of dry air per cubic meter total, so cubic meter moist air. And the wet density is kilogram of moist air per cubic meter of moist air. And you have these equations here. So raw dry equals the difference between the total pressure and the partial pressure water, since we deduct the water to get how many kilogram of dry air we have. So it's essentially the ideal gas law, but we take away the water. And this one instead, the wet density, you calculate it in a slightly different manner. And the reason here is, well, you have to think about this for a while to derive this equation, but it has to do with the molar masses. So 29 here is the molar mass for air, and this is the number you get once you shuffle around. But anyway, let's see what that means. This is a density diagram. You have two x-axes here. The upper one is for the wet temperature, going from -20 here on the left to 80 on the right, and the dry density here going from -20 degrees on the right to 80 degrees on the left. And these lines here are the dry density lines, and these ones are the wet density lines. And as you can see, you get different densities depending on what kind of moisture you have, what kind of relative humidity you have. It might be noted here that if you have no water, then the lines are actually identical. But if you have 100% water, you get quite a large difference. Okay, what can these diagrams look like? Well, this is an example from Flecht Industries. They created a diagram where you have most of the things here, and then you have a separate diagram down here for the densities. But note here that this is upside down compared with this one. So be careful when you use this, because the density decreases as you go up. There is something we haven't talked about in this diagram. That's these numbers out here. But I would recommend you to ignore these totally, because they are not related to anything we do in this course. There is another way to draw psychrometric chart, and if you study in the US, you will get more used to these kind of diagrams. They essentially show the same thing. It depends on who draw the diagram, what kind of lines there are, if density is included or not, or if water content as kilogram of water per kilogram of dry air is included or not. But they might look a bit different. In the one used in Sweden commonly, a good thing is that it's equal distance between all the water contents here, and it's equal distance between all the enthalpy lines. And that's very handy when you do adiabatic mixing. We'll come back to that later. Okay, time to go into heating and cooling and dew point. If you heat or cool an airstream, then the water content is constant. And that means that you have a vertical line in the Mollier diagram. So if we warm this air here, we simply go straight up to a new point. Now, there is something that's called dew point, and if you have a moist air and cool that, you might reach a point where the partial pressure water, which is constant as you cool it, becomes the same as the vapor pressure. And that temperature is called the dew point. If you cool any further, then water will start to condense. So let's do an example. Temperature is 40 degrees Celsius and you have a relative humidity of 0.2, so 20%. What is the dew point. Okay, 40 degrees and 20%, that's there approximately. And then you go straight down, and that's the point here, and you have about 13 degrees Celsius. If you cool below the dew point, water starts to condense, and you will follow the dew point curve, so the curve for 100% relative humidity. So you go straight down, and then you follow the 100% line until you reach the point. So how far do you go? Well, you can look at the enthalpy lines and compare this enthalpy here with this enthalpy down there. This is in kilojoule per kilogram of dry air. So if you know the air flux in kilogram dry air per second, for example, you can calculate how much energy is needed to cool down to this point here, and then you can calculate how much water you lose. You can simply go up here and see what the water content is now. Cooling and warming, you have vertical line in the Mollier diagram because x is constant. If you cool below the dew point, you first go vertically and then you follow the dew point curve. And now we're going to talk about adiabatic mixing of air streams. So you have a warm air and a cooled air, and you mix them, and you can write up mass balances. You have mass balance for pure air and mass balance for pure water. And you can also write an energy balance. And the thing is that the mixture here, G3, will be on a straight line between G1 and G2. And that's because we have equal distance between different water contents and equal distance between different enthalpy lines in the Mollier diagram. Let's do an example. A 1 kilogram dry air per second airstream at 25 degrees Celsius and 40% relative moisture is mixed adiabatically with a 3 kilogram dry air per second airstream at 47 degrees Celsius and 40% moisture. What will the status of the mixture be? We're going to solve this example without the Mollier diagram at first, and then we look at the solution in the Mollier diagram. So we make a mass balance. G3 equals G1 plus G2. That means 1 plus 3 equals 4 kilogram of dry air per second. Now we want to have the water content X to be able to make the mass balance for water. So we know that we have the relative humidity of 40%, and we know that we can calculate X if we have the partial pressure of water. So let's use Antoine's equation to calculate the vapor pressure. So we look up A, B, and C in a table, and for that table we need T as temperature in Celsius, and we can calculate the vapor pressure to 32 millibar for 25 degrees Celsius and 106 millibar for 47 degrees Celsius, which means that we have a partial pressure of water as 12.8 millibar and 42.4 millibar, since we have 40% in both cases. So we can calculate X using this equation here, and we get 0.62 times 12.8 divided by 1013 millibars minus 12.8, and we get 0.0079 kilogram water per kilogram of dry air at 25 degrees, and the 47 degrees air has 0.027. Now we can make the mass balance for water, and we get 0.024 kilogram of water per kilogram of dry air. Note here that this was G1 times the water content in G1. Okay, so that's the solution, but we can do that in the Mollier diagram as well. Adiabatic mixing, so we find the hot air, G1, 40% is this line here, and we know the temperature, so we can easily find 47 degrees there. The cold one is down here, also 40%, and instead 25 degrees, and then we draw a straight line in between. And the resulting mixture should be on this line. And we can use the mass balance we had before, since now we can actually see here directly what the water content is in this case and in this case. Now, I should say that this Mollier diagram is a bit sloppy. It's drawn for simplicity, so that it's easy to see in the screencast, but you should be using a more exact one when you do these calculations. Anyway, you use the mass balance and then you find the point here. So these are the mass balances. The dry air G3 equals G1 plus G2, and the water one, where we now have found out the water contents simply by identifying the points in the diagram and then looking what kind of water content we have. You can do another thing here. You can do an enthalpy balance to make sure that you have the right points. You go down here and see what enthalpy you have. Parallel with these, the 40 enthalpy line here, you go down and read what kind of enthalpy you have. And when you do the enthalpy balance, you should end up with an enthalpy that is also on the line. What you probably have seen here now is that the graphical solution in the Mollier diagram is fast. We didn't have to go through all that hassle with all those equations to find how many kilogram water per kilogram of dry air we had. It might not be that accurate. For one thing, it doesn't actually take into account that we have different heat capacities at different temperatures, but to do those calculations by hand accurately, well, that's a real pain anyway. The numerical solution might take some more time, but it might be more accurate if you are careful with intermediate results. If you're sloppy, for example, when you calculate the vapor pressure and so on, and don't write up enough decimals, you will get non-accurate result. And numerical solution is tedious if you want to do it exact, since both evaporation enthalpy and heat capacity varies with temperature. But on the other hand, most Mollier diagrams are actually drawn for constant heat capacities anyway. So the last thing we're going to talk about today is air conditioning. If you, for example, have air conditioning in your car, what happens then is that outer air is mixed with air from inside the car. So you have G1 and G2 here, and you mix those and end up with a mixture in between here somewhere. The G3 here has far too much water in it, so we cool down that to the dew point, and we continue to cool it down even further to lose some water. Then we want to get to this temperature again, so we take part of the G4 and heat that all the way up to here, and then we mix G5 with what remains of G4 to get to the same point here. So this is at steady state when we have reached a comfortable temperature and just want to remain at that temperature. The non-steady state problem is a bit more difficult to handle. To summarize, we have seen how you can use the Mollier diagram to analyze changes graphically. We talked about the wet bulb temperature and the adiabatic saturation temperature, and for air water, the wet temperature is approximately equal to the adiabatic saturation temperature. And we have seen when you do adiabatic mixing that you take energy balance and mass balance to calculate the mixture.